Hello students, welcome back. Third section, determinants as areas and volumes. This is not that important in terms of linear algebra alone, but if you combine this with analysis, this is humongously important because this is the backbone of Jacobian determinant computation that applies for multivariable calculus and vector calculus. When you have multiple integrals, then the volume element or n-dimensional volume element is basically the determinant of the Jacobian matrix, the derivative matrix, and that's related to the fact that determinant is actually area and volume of parallelepiped. Here's a reminder. Let phi be a real function with n-dimensional vector variable with the following properties: multilinear, alternating, and identity property. Then this is determinant. The proof, that's too complicated and that's too deep, so I'm not going to do it. But remember this uniqueness because we're going to be using the uniqueness to explain the areas and volume kind of thing. Okay, here we go. Let A1, A2, A3 all the way over to AN be column vectors. Then the volume of the parallelepiped determined by these column vectors is the absolute value of the determinant. That is, if P is this, where all the coefficients here, excuse me, sorry about the typo. Everything, x1 through xn are between 0 and 1, then the volume of this parallelepiped is the absolute value of the determinant. How do you do this? Well, we introduce the concept of oriented volume and allow the volume to have negative value, and then we're going to prove that oriented volume satisfies these three properties. Okay, here we go. D3 is trivial. If you put in identity matrix here, then what do you have? We have a determinant of identity matrix is 1, so the absolute value is also 1. As for parallelepiped, it's just a cube, n-dimensional cube. So that's trivial. And then let's look at alternating property. If you have two identical columns, what do you mean by that? It's flat. So we are losing a dimension. So what is three-dimensional volume of a two-dimensional parallelogram? And that, of course, is 0. What is two-dimensional area of a line segment, which is one-dimensional? Always 0. So alternating, that also is 0. No problem there. Now, how about multilinear? With respect to one direction, if you add, so this is sum and this is red plus blue, and you're simply adding the areas. Green area is red area plus blue area. So yes, preserves addition. And then how about scalar multiplication? Multiply by c. In this case, c looks like a bit negative. So this is whole. And then I reduced a little bit. C times of this length. And what happens to the entire area? C times the area, because everything else stays the same. And that applies to the n-dimensional cases as well, so no problem there. Except, what if C is negative? In that case, we have to consider oriented volume can become negative. If you put negative out there, put negative. And consequently, we can consider alternating property with negative of volume coming up, because we are dealing with oriented volume from now on. Then we have all those properties, multilinear as well. Therefore, by uniqueness, it's a determinant. And of course, if you take the absolute value, then the orientation, that part is gone, and we have the volume element. That's about it. And did I assign some homework problems about area computation? I think I did, but it's no big deal. Just calculate the determinant and that's it. As for any kind of proofs here, no, I'm not gonna go there. It's not really a core topic, and it's more tedious than difficult. So I'm stopping here. The others are just exercise problems.